Thanks for the introduction and very enjoyed the presentation of Dr. Noble and Dr. Moch, and they give a very high-level summary of the opportunities and challenges with critical mineral recovery. I think with their presentation, actually, mine will be easier. So my research group actually has been focused on critical mineral recovery for many years. And in this presentation, I'm going to introduce some innovations that we made actually in this area to address some challenges and to discover some new opportunities. Here, okay, all right. So my lab actually, we use different expertise. So basically we use advanced characterization, we use mineral processing, extractive metallurgy, chemical processing, and also green chemistry and material science to develop new technologies and new process to address the challenge with critical mineral recovery from different feedstocks. And most of the feedstocks are non-conventional. Yeah. And we focus on different feedstocks. For example, primary feedstocks, industrial waste, and secondary feedstocks. And in summary, actually, we can categorize into two different types of feedstocks, solid form and liquid form. In this presentation, I mainly focus on liquid form or secondary feedstocks. So in terms of liquid forms, actually, we have different types of aqueous feedstocks actually for critical mineral recovery. For example, acid manganese, produced water, geothermal bronze, all these actually belongs to the secondary critical mineral resources. And I think there are many opportunities there, but there are also difficulties. For example, the most common issue is low concentration of critical minerals and also the high content of contaminants. Just like Dr. Moch said, actually, selectively recovery of low concentrations from dirty aqueous streams, that's challenging. Just like actually when we do the mining, we have cutoff grade. If the grade is below the cutoff grade, most of the technologies actually cannot support economically viable extraction of the ores. The same as the critical mineral recovery from secondary feedstocks actually. If the solution actually is very dirty and the concentration of critical minerals is too low, actually the existing technologies cannot support economically viable extraction. Yeah. Here example, for example, in produced water, which is major focus in my group right now, the lithium concentration is less than 100 ppm, which means in 1 liter of produced water, you only have 0.01 gram of lithium. But the total dissolved solid actually is larger than 10%, which means in 1 liter of produced water, the salt content is larger than 100 grams. So how to actually separate and purify lithium from such a complex feedstock is challenging. Okay, so I want to introduce some technologies that we developed actually to address this issue. The first one, we call it a state precipitation or sequential precipitation. Yeah, this was developed sometime in 2018. So basically, when we work on rust recovery from acid leaches from coal-based materials, we run into an issue. The rust concentration is very dilute. I mean, it only contains around maybe a few ppm level, which is very dilute here. So if you use some injection directly applied actually on this stream, it's not economically viable. So what we develop is that we can use precipitation. So basically, you can collect the precipitates formed in certain pH rings, and then you are going to get a pre-concentrated precipitates. And then actually, you can redissolve the precipitates. You can increase the concentration up to gram per liter level, and then actually the downstream processing will be economically viable. So this process is easy, and the operation is also easy, but we also notice some issues. You are going to consume a lot of acid and base during the precipitation and redissolution process. And after that, actually, what we develop is that we integrate of cobalt, nickel, manganese, some other critical mineral recovery in the process. And this also gets successful. We also finished the pilot testing of this process. Again, actually, as I mentioned, actually, you are going to have a lot of chemical consumptions. Just recently, actually, we did a study. We call it a coupled chemical sorption and electrosorption recovery. So the function is very simple. So basically, you put the two driving forces, chemical sorption and electrosorption, in one system. The key is how you design the electrode materials from the physical and the chemical aspects. And then actually what we found is that we can achieve the trace elements recovery. As you can see here in the recovery figure, actually, we can achieve almost the 100% recovery of REE as dilute as 1 ppb level, so which is pretty promising. The reason at the beginning, actually, we are pretty reluctant actually to do electroabsorption because we know that there are costs associated with electricity. But when we realize that actually electrochemical absorption has been widely used for lithium extraction, it has been commercialized. And then actually we transfer to this topic, we started some exploration here. And then this topic is, we call it gas-assisted microbubble extraction. And when we do rare recovery from coal, actually, Dr. Noble did a lot of techno-economic analysis. And I was told that actually, if you want to get economical benefit for rare recovery from the coal leachate, you are going to need actually very high aqueous to organic volume ratio. This also makes sense because when you use a very high AO ratio, you are going to generate a very small volume organic phase. This can save your capital cost and also the downstream chemical consumptions. But when we tried soil injection at a very high AO ratio, the issue is that we have a difficult time to get the organic phase uniformly dispersed in the aqueous phase. And then actually the extraction kinetics is very low, extraction efficiency is low. What developed is that we call it a game. So basically we set up a very simple apparatus. So the apparatus can generate organic phase coated air bubbles dispersed in the aqueous phase. In this way, you can reduce the mass transfer distance and also increase the mass transfer rate. And even at an AO ratio up to 50, so we can still get a very good recovery. So this technology actually has been licensed to Phoenix LLC, and the founder and CEO Dr. Das is also sitting in the audience here. So Dr. Noble actually mentioned a very good point is the traditional value chain. So when we work on critical mineral recovery, we need to actually focus on not only get rid of the contaminants, we need to think about how to use the contaminants. This is a very good example. Produced water, we have a lot of lithium, we have some lithium, but we also have a lot of calcium, magnesium. So we did a study that we use the produced water to fix carbon. And we found that 1 ton of produced water, we can fix up to 30 kilograms of CO2. And we can realize the carbon potential of 90%, which is pretty encouraging. And after that, actually, we did a more comprehensive study. So we integrate rare recovery, strontium and barrier recovery, carbon fixation, and lithium recovery into one flow sheet. And from this flow sheet, actually, we can generate a lithium carbonate product with better grade, 99.5% pure, so which is already can be sold as a commercial product here. So during this process, when we use, for example, when we do this carbon fixation, we can remove calcium, magnesium actually using CO2. But we also need to add some sodium hydroxide actually in order to maintain the pH value and then maintain the weekly alkaline pH conditions. And then actually, as a result, we introduce a lot of sodium. So the good thing is that if you check actually, the lithium separation from sodium is easier compared with lithium separation from magnesium. Because magnesium actually, the ions has a closer analytical radius to lithium compared with sodium here. And then actually for lithium and sodium separation, we develop a synergistic extracting system, which realized actually a separation factor of 10 to the power of 4, which is pretty encouraging. So basically we can get almost 100% recovery of lithium, and then actually the sodium extraction is pretty low. It's almost zero, yeah. So direct lithium extraction. Conventionally, actually, when you recover lithium from bronze, you need to use solar evaporation to concentrate lithium to get rid of some contaminants. So direct lithium extraction is more popular now because it has a small footprint, and also it does not have the issue of the production, because conventional lithium extraction, the production is very sensitive to signal change there. Direct lithium extraction does not have this issue. So for direct lithium extraction, absorption actually is one of mostly widely used technology because it has low operating cost, low energy consumption, and there are 3 types of absorbents mostly used for direct lithium extraction. I list the 2 here, titanium-based and manganese-based. So these 2 absorbents actually has not been commercialized. The reason is that actually their cycling life is pretty low, especially when you do the desorption. You need to add a lot of acid to dissolve the lithium from the absorbent, and this will cause the dissolution of manganese and titanium and the destruction of the structure of the absorbents here. As a result, actually, our group focuses on aluminum-based absorbents. Aluminum-based absorbent, it has low absorption capacity, but the good thing is that it has a very good cycling life. So that's the reason why aluminum-based adsorbent is the only commercialized adsorbent in direct lithium extraction. So we tried direct lithium extraction for lithium recovery for produced water, and we get some continuous running data. If you check the data on the upper right corner, as you can see, the feed contains around 100 ppm of lithium, but with the continuous direct lithium extraction with aluminum-based adsorbents, we can generate a lithium concentrated solution with a concentration around 900 ppm, and then as in the raffinate, lithium is almost zero. So which means direct lithium extraction works. But our issue is that actually the adsorption capacity is pretty low, and also because the dirty of produced water, actually the structure of aluminum-based adsorbents also damaged after running for a certain period. So focusing on this, actually we are trying to modify aluminum-based adsorbents chemically and physically. The first thing we do is that we incorporate polymers into the aluminum-based adsorbents, which can actually change the local adsorption environment. In this case, actually, we can increase the absorption capacity of lithium. Okay, so the first adsorbent as a polymer we use is PAA, and we also tried PEG, actually, which is also very effective. Yeah. Sorry, yeah. So after chemical modification, actually, we also tried physical modification. If you check the figure on the right side, as you can see, typically, actually, we generate, we will synthesize aluminum-based powder, so it's in powder form. So in the industrial application, you cannot directly load the powders in the adsorption columns because the liquid will not percolate through the column if you put powders into a column. So the industries, what they do is that they will, the powders need to go through a granulation process. In this process, they are going to add some binders, and they actually generate some granules through extrusion. Yeah. In this process, what happens is that because you convert from powders to granules, and then actually the absorption capacity is typically reduced by 50%. This is also easy to understand because some powders actually inside the granules, they have very slow absorption kinetics. Okay? And then what we did is that we tried to replace the granulation process with something like electrospinning. So we use electrospinning actually to produce non-absorbent fibers. It's a membrane, and also the membrane consists of many actually nanofibers. In this case, each powder particle is exposed to the solution, and you are going to have very high absorption capacity and also absorption kinetics. So what we found is that we can achieve absorption capacity of almost 14 milligram per gram, which is much higher compared with conventional aluminum-based adsorbents. Yeah. So this is something that we explored, and we also tried 3D printing to print out adsorbents, and we just got successful recently. Yeah. So this is another study actually. So basically we set up a very simple apparatus, and the apparatus actually use new material. This new material has bilayers. In the top layer actually is photosensitive, which means it can absorb solar energy. And the bottom layer actually it can have lithium selective absorption capacity. And what we found is that actually it works well, and it can achieve the function of desalination and lithium recovery simultaneously. And we also found that actually at a very high solar energy, for example, at 600 watts actually, we found actually absorption capacity dropped, and we conclude a mechanism of hydration controlled lithium absorption. Yeah. So this is a very good finding because conventionally we saw the lithium absorption is chemical driven, but we found that actually hydration is also an impact factor as that will affect lithium absorption, and we are trying to do more research in this area. So that's my in-the presentation, and thanks for the groups from Missouri Science and Technology for the workshop. And we have several patents, and acknowledge the funding from DOE, and also acknowledge the support from my collaborators such as Dr. Das and Dr. Noble, and also acknowledge my group members. That's all. Thank you. Yeah.